I'm very excited to introduce our last technical speaker before we embark upon some curriculum-related talks on how you can actually do this in high school. But we felt it was very important for you to at least have some fundamental understanding of quantum physics and quantum computing before we get to this point. So you may think that so far quantum computing is very abstract. So our next speaker is really the perfect person to illustrate how these ideas are actually coming to fruition physically in the Southeast New York region. So it's my great honor to introduce my colleague, Dr. Eden Figueroa, to talk about the quantum testbed network on Long Island. Eden.
Hey, thank you, Angela. How's everybody doing today? First of all, I would like to say this. Two of the most influential persons in my life were my chemistry teacher in high school and my German professor that taught me quantum physics in the first year of my undergrad. And they really changed my life, and this is why I'm actually here. So thank you for being here, and thank you for educating. That's the most important task that we have these days, all right? So let me tell you a little bit about the stuff that we're building here on Long Island, because I think this is something that all of us, we should be proud. You know, I guess since the F-14s that we were building here, there was maybe not something so perhaps large. So now we're trying to build this, and I want to thank Dominic for doing the hard task of trying to explain quantum entanglement. So I'm going to assume that everybody understood quantum entanglement and that you're experts on this, on what I'm going to tell you. All right? So first, maybe I would like to start with a slide that shows a little bit how our internet works. I think we all can agree that one of the most important technical realizations that humanity has ever been able to do is just creating the internet. Right? And then thanks to this, now you can exchange your Instagram and Facebook picture with your friends, which is probably a great thing to do, all right? So I'm just lining up here a few of these very important technical achievements that humanity has done, right? So we actually learned to encode information in the form of bits, yeah, nothing quantum here, just classical. And we also make a big investment in the late 80s, early 90s, et cetera, where we have companies all over the world put fiber optics connecting academic institutions, financial institutions, banks, et cetera. So then now we have an interconnector world, and basically all the different big institutions that exist have fiber optics connecting them between them, and that's how we have the backbone of the internet, right? That started in 1983. So taking a trip down memory lane, how does the internet actually started, right? So the internet, there's several theories, but one of them is that it started here in the United States in what is called the ARPANET, right? The ARPANET was a collection of institutions, military, academic, national labs that started interconnecting their campuses in the Boston area together with a series of academic institutions in California, right, that started connecting this. And what was important at the time, it was they devised a system that allows to identify where you are. Maybe you heard the concept of an IP address, right, which is in your computer. Maybe when it doesn't work, somebody comes and says like, oh, your IP address is wrong, therefore you have to change it so then you can connect. So the IP address tells the computer, right, when it starts emitting information, and then it goes into switches and routers all across the world where that information needs to go, which is based on the IP address of another computer that is at the end of the line, right? And basically the way it actually works, this information that the computer is sending, for example, in the form of your email, is just basically encoded in laser pulses, right? So basically what your computer does, it just starts emitting, right, information, and then eventually at some point, there is a little laser that transfers this classical information into pulses of light, right? And so what happens there is like the whole system that we have, for example, if you want to send an email from your friend in Europe, et cetera, right? These lasers are going to these fibers that we just described, and then as the information gets attenuated in the fiber, you have amplification points every 50 miles, right? So many people don't know this, but every 50 miles, there is somewhere hidden in a side mall or something, a data center where you have amplifiers, they amplify the information, so it can actually go from reaching just a few miles into reaching thousands of miles across oceans, right? This is actually the backbone of the internet. However, here is where the problem lies. because in the internet, the fact that we have to amplify the information for it to actually reach where we want comes with a problem that you cannot differentiate between the normal losses that the information undergoes in the fiber and somebody eavesdropping on you. Literally, it's the same. At the end, the amplifier doesn't know if you lose it in the fiber or if somebody is sneaking, right? And this is why if somebody hacks your computer across the internet, right, you don't know about it until somebody publishes it in TMC website or whatever. Right? This is exactly the reason, and to some extent, the main weakness of the internet, right? This is very important because we don't have a solution for this, right? Additionally to this, right, because, right, the information in these laser pulses is flowing across fibers, right, we suffer the same thing that we suffer when we drive in 495. If there's too many of these laser pulses at the same time, then you get a crazy bottleneck. It's like trying to get in exit 19 out there when you go to New York City. It's almost impossible, right? So that's another problem, right? We clog information that is transferring in these fibers, right? And then, you know, for some other things, the internet is good, for example, to transfer video, or for example, if you're doing your Netflix stream, no problemo, right? As long as your synchronization is not required within less than 1 millisecond, which your eyes are not sensitive to, nobody notices. That's okay. But if you want to do very sophisticated time and synchronization protocols, finding bad people across the earth, etc., you need to keep building on this to make it more precise. Right? So these are I have it here as the internet to-do list, right, that we need to do in order to keep improving and keep making it, you know, the best thing that we have. And then here is where I'm going to connect to what Professor Schnebel said, right? One of the answers that we have established to do this is basically, okay, what if instead of doing laser pulses that contain millions and millions of photons at the time, right, and then, you know, we use the amplification system, what if we completely change the paradigm and then we use what Professor Schnebel explained to us, which is, let's use quantum particles. He explained the concept of photon, right? Why don't we use photons? Because then photons are now allowed to go into quantum superpositions, and we can actually create entanglement, just as he talked about the cats, right? Well, I guess maybe PETA is not going to allow us to use cats for this experiment, so we'd rather use photons, right? So then, if we can create these photons that have superpositions and entanglement, and we can use the backbone of the internet that we already have, we can then start transmitting entanglement. And then I tell you what are the things that we can do with this. So what I wanted to do here is to give you like a mini lab tour where you can see how these experiments are done. So what you have here in the video, right, it's an entanglement source. This is a system that creates photons and then makes them in a superposition, or it also creates entanglement between two photons, so then we can distribute them across long distances, so then we can do a series of experiments, right? So this is what people call an entanglement source, right? So imagine that there is like a big cat that is giving birth to two Schrodinger cats, right? And they are in a superposition and you don't know which one is which. That's exactly what this machine does. And then, you know, you see it here, you can actually see you can follow the path of the laser. Laser goes in there, hits those two crystals that we have in that copper mount, and that is exactly where the magic happens. We create these two photons, right? And then just by manipulating them with some optical elements, we can actually create these states where if you have one photon going to one place and then you do a measurement on it, then the photon that travels into the other place, it will react to it, right? And this is what is called spooky interaction at a distance, as Einstein wrote it in his 1927 paper, right? Let's try to do this spooky interaction at a distance here on Long Island. Yep. So what I was telling you is if you can do this, then you can start doing information processing in a different way. As Professor Schnebel told us, if you make a measurement in one of these photons, then the other one will react, which is going to be the tool to know if somebody is eavesdropping on you. So if you're sending this entanglement in the fiber, right, that contains this information, and then at some point somebody eavesdrop on it, as he just said, it makes a measurement on it, then the other photon will feel it, and this is what is called the quantum alarm. Quantum gives you an alarm that knows that the eavesdropper is getting your information, right? So this is how we're trying to solve these big plug holes that the internet has. Additionally to that, we have something, and maybe, I mean, you're physics teachers, so I assume all of you like Star Trek. Please tell me you like Star Trek. And tell me that you like it more than Star Wars, but anyways. So in Star Trek, you remember, Captain Kirk is going to tell beam me up, Scotty, right? Which means it's going to be teleported from one place into the next. What transporting entanglements allow us to do is to do this beam up photons of information. So if you have this, you can use a process that is called quantum teleportation to move this qubit information that Professor Schnabel defined, and then using entanglement, we can move those qubits. By doing this, we define a different highway of information that doesn't clog like the 495 highway, right? Because now you're teleporting it, so you're not clogging the information in the fiber. It's actually moving somewhere there in some subspace, right? That we have infinite resources, so then we can move it, right? And then, additionally to that, as Professor Schnabel say, we can use this internet that has entanglement to then connect quantum computers. And then just as Professor Tsuchiwe told us, we can then make super quantum computers that can help us simulate all kinds of things that normally, with our current computational power, we cannot, right? So it's all cool stuff. Here is something that connects to Long Island, yeah? Many people don't know this, but the gateway of the internet in the United States is here on Long Island, right? Like, for example, I guess these days we don't want to be friends with Europe, but whatever, let's ignore that. Let's just say that if you have friends in Europe and you want to exchange an email or have a video Zoom call with them, the information has to flow in these fibers. The three main fibers that go from Europe to the United States enter in Greenport and the Hamptons. If you didn't know, that's exactly right. And as we say before, as these fibers enter Long Island, yeah, every 50 miles or so, we need to have these data centers where we have to amplify the information. So then it makes its way all the way to that point in there that is called the Manhattan Land Exchange. The Manhattan Land Exchange is a skyscraper in Manhattan that has no windows. All the windows are covered because inside, all what you have is switches, servers. So then they take that information that is coming from Europe and then transfer it to the main hubs in the United States, in Chicago, San Diego, the Atlanta area, etc. Yeah? So then it actually makes sense that we start making this quantum internet here on Long Island because we have all that fiber already, right? So you don't have to invest, it's already there. All right, so now let me tell you what we're building, right? Which is, it's gonna use the backbone of that fiber, right? And then what we're gonna do is, we're gonna put some of these experiments where we create entanglement. For example, the one that I show you there, we install it in our laboratory that we have in Brookhaven National Lab, over there in Upton, New York. That's the beginning where everything is, right? And then what we're doing in the last few years, we're taking that fiber and we're working with local fiber companies to start establishing nodes, right? In which instead of amplifying information, now we have quantum technology that allows them to characterize the superpositions and the entanglement that we are transmitting in these fibers. So then eventually we can do the connections that Professor Schnabel and Professor Tsuchiwe told us about. So here is, as the bird flies, as they say, if you're an astronaut and then you want to look where the first internet in the United States is being built, well then you just go there and boom, we get there to Long Island, and then you see the 3 points where we're doing the entanglement. So that entanglement source is in Brookhaven, right? All the way, in this case, to my left, right? In Upton, New York. Then the green things that you see here are fibers, real optical fibers that are used to transfer information classically, but now we're using them to transfer quantum entanglement. The first of these fibers connects Brookhaven to my laboratory here in Stony Brook in the physics building, and the other one connects the Brookhaven lab to one of these data centers that we have in our picture. So we went there, I'll show you some videos, we made some crazy things, and then now the Long Island data centers also have quantum hardware in them, right? So this is how this looks from the air, right? Technically speaking, literally what we have to do is we had to build a better internet, internet that is faster, an internet that is more precise. This is just so then we can control the entanglement that is created, and then we can tell whether or not we are preserving these quantum properties across long distances, right? So it was like a big effort, bunch of engineers, like 12 grad students. This is what they do, right? And they do it at night because otherwise you will see that we might bother some people. All right, so here is basically, remember I showed you already how the entanglement sources look like and how is that we create this photonic entanglement. So then what I'm showing you here is one of the end nodes, right? What is that, exit 23, I think? If you go in the Northern State Parkway, first exit after Smithtown, you get Comac, right? There is like a really big Stony Brook medicine. They seem to be everywhere these days. Big Stony Brook Medicine Complex. At the back of it, nobody knows this, but now you're going to know, is the biggest data center on Long Island, right? The biggest data center on Long Island. There's a picture there. So the video that I'm showing you now, if somebody asks you, how does the internet look like? The internet looks like that guy, that video that you see there, right? It's a collection of servers, computers, amplifiers, everything. And inside these racks, what you have is these amplification systems that, as I was telling you, amplify the information so it can get to you, routers, so then it can be to any house where you need the information to be, etc. So then what we did is, about 2 years ago, we started building a mini quantum laboratory in this data center. So the video that I show you here, remember what Professor Schnebel told you, you need sometimes cryosystems that allow you to lower the temperature of this, such that then those systems are so exquisitely sensitive that then allows them to detect the single photons that are carrying entanglement. So then what we did, and maybe I think this is kind of crazy, we actually put a cryo system that is pumped with cryo-cooled helium, right, that is cooling some detectors so then we can detect entanglement. And this is right beside your internet. So if your internet goes down, it was probably us. But anyways, don't tell that to anybody, okay? Just to give you an idea, we have a flood problem one day, and then one company came running like, oh my God, there is water close to our servers, so please don't do that. Anyway, so this is a detector, right, that then allows to detect those photons that are arriving to the COMAC node. We have a similar detector in the Stony Brook node. And then what we want to do now is, once you have detecting these photons on both sides, you actually want to show that they have entanglement, right? So then some of the things that we have done in my laboratory recently, this is going to be one of our last slides, right? This can put it all together. And then so I'll run by you what we have here in this place, right? So here on the right, we actually have the classical internet, right? Basically, we're running a bunch of code. And what this code does, it uses classical information that is moving across these fibers to then control quantum experiments so we can produce entanglement, and also to do the detection systems and understand what the detection systems are telling us to then demonstrate if entanglement is done, okay? This is what this part does. Now, here you have some videos, right, that show you the Brookhaven node, the entanglement source that I show you. You will see when I run the video that this is going to lit in red. That means that we're pumping lasers, so then we are creating entanglement, right? And when we pump the lasers, here we have the signal in those detectors, these cryo detectors in COMAC, and here in Stony Brook. And then what you will see is that when we pump with the laser here, the photons start flying in the fibers, and then you will see that there is a count here, right? Additionally to that, right, we have to do some measurements that allow us then to know whether or not the entanglement that we're sending, it is of good quality. So then you will see that sometimes these two pictures here, which are our measurement stations, they also lit red. That means that we're doing some measurements to then determine whether the entanglement is good or not. All right, so let's run this. This is like, imagine that I took you to the lab, and then you're seeing exactly why my students are getting PhDs and whatnot, right? So you see it here. Notice that this got lit, and the moment this got lit, we got signal here. What that means is that we are transmitting entangled photons, each stream across 70 kilometers, a total of 140 kilometers. And then you see that at sometimes this part lits. This means that then we're doing measurements to then guarantee the quality of the transmission of entanglement. Notice that when this stops, right, there is a mirror here that then moves. You see it coming out of the picture. When this comes out, then that means that then photons are flowing again. So then we can do our measurements, and then we can do our detection, right? Fun fact here, as I was telling you, the classical internet requires about time precision of about several milliseconds. These experiments that we're doing here require a precision of 100 picoseconds. That means that we have 7 orders of magnitude better classical internet just to be able to then determine these entangled photons. The good news, and this is something that happened in October last year, for the first time in the US, we have made an experiment where we transmitted entanglement across more than 140 kilometers. Happening there at the backyard of your at the backyard of your house, right? So anyways, at some point, you know, if you have time and you want to see it, we can show you the lab in some other visit that you have on campus. Let me just close this so I can finish this story. This is not the end of the story. This is just the beginning. This is what I always tell my students, so prepare for this, right? Now we are expanding this network. Remember, there were 3 nodes. There was Brookhaven, there was Stony Brook, and then there was Comac. Now we're basically taking over Long Island. Why not? And then so now we are going into other data centers, installing more quantum equipment, and then doing even more daring experiments to try to see if we can now distribute entanglement to the city of New York. That's our goal for the remainder of this year. Now you see it here, the examples of the things that we're building. Westbury, the old city of Westbury, now we have a data center in Westbury. This is exactly how it looks like. You see the video, very similar to the one in Comac, where now we are building, you see here on the left, we're building another entanglement source, like the one we have in Brookhaven, that we're gonna be deploying here in Westbury in the next couple of months. We also have another data center in the Brooklyn Navy Yards. If you haven't been there, it's pretty hip. There's good restaurants, so it's reasons to visit. That's where we have the end node in New York. And the idea is to transmit entanglement across 250 kilometers between the Comac data center and the Brooklyn Navy Yards. The largest experiment of its kind, we think, in the world right now. Yep. So that's pretty cool. And you know, just because it is important to do this, we have to acknowledge that we are doing all this expansion of our quantum internet using a grant from the New York State government. If you go on Google and you check Governor Hochul Quantum Internet, she will actually explain you the project in a 1-minute video, right? She's very nice. So now what we're doing is we are expanding this quantum internet to reach other institutions. We are now procuring the fiber that is going to connect the Brooklyn Navy Yards, where the entanglement ends, to the laboratories of several professors in Columbia University. And we're also building, next time you drive around here, please look at the top of the Health Science Tower, the hospital in Stony Brook. We are building another mini lab in there, and then we are installing some telescopes so we can actually send entangled photons across the air over the Long Island Strait all the way to Yale University. In this way, we're going to have all the most important academic institutions and national laboratories connected with entanglement, so then we can eventually realize the dream of connecting quantum computers with that quantum internet. Lastly, and this is why we're all here, in order to do this, we cannot do this alone. We need students, we need workforce, we need you guys to motivate the high schoolers, so then eventually they come and work here with us, right? So this is why this event is so important, because if you guys don't work with us, we will never make this happen. So when you teach them, tell them what we can do with this. As a matter of fact, if we can build this internet, right, now we can confront some of these biggest problems in physics that sometimes we have not been solved, such as, for example, the relationship between quantum mechanics and gravity. Big problem there that has been, people have been tackling for decades, right? We can look into how entanglement actually changes space and time. Imagine this, we're actually changing space and time on Long Island as we transmit entanglement. If we could demonstrate this, oh my God, wow, right? We can do some astronomy experiments that right now cannot do. We can explore whether or not entanglement actually creates black holes. There is so much plethora of experiments that we can do, and all this can happen if you help us motivate students to become quantum physicists and work with us. So with this, I leave it to you. I hope at least I motivate you to go and tell your students, this is so awesome, please go and do it. And I'm very happy to take some of your questions, and thank you so much for your time.
This is really a fantastic application, and right here on Long Island, nowhere else in the United States, so right in our backyards, as Aidan said. Yes?
I was wondering, do you foresee any issues with expansion using the fiber optics cables? And not to rush you, but have you thought about any wireless applications for the quantum?
That's a great question. So say, there is always problems with expanding because somebody has to pay for it, so that's the first problem that has to be solved. But say, as insofar, now we are developing some plans. Actually, you heard from our SUNY VPR Shadi, that is there in the back. We have now plans to expand these all the way to Albany, Rome, New York, the Air Force Research Lab. So then it's all a matter of infrastructure. Is the infrastructure ready to deploy these things? And you know, there's some technology that still needs to be developed, so then we can do this over longer distances. So this is 10 to 15-year project by the time we develop the technology. RF is good, and actually in the experiment that we're doing with Yale, must be used, because in that experiment, because it's in the air, The photons will go in the air, but everything that is necessary for the experiments to run has to work with RF. So RF is also involved. The only, say, caveat there is that we don't know how to make photons in the RF, so then quantum applications in the RF do not exist. However, the RF is used for everything else, control, classical internet, etc. Yep. Thank you for your question.
Yes. Eden mentioned the company QNECT that works with him. Those are actually former students from his laboratory. And these are the types of startups where the individuals tend to be very interested in speaking with high school students. So we've had some of these workers from startups speak to our summer camp students, and it's actually been quite motivating for students to understand what a job in that field is going to look like. So I think QNECT would be interested in connecting with schools along with other startups in the region.